So for those who have joined now, Chandrasekhar has asked a question, so I'm just trying to answer it. We'll start in 5 more minutes. Okay. So question number 31 you are saying. Let me see what is that. Okay. One-sided abrupt junction direct depletion. Okay, so this one I think the depletion capacitance formula is there, right? So in that I think the depletion capacitance is dependent on a square root of something. So that is why they have given CD square value with respect to V. Okay, and then you have to do the like give the slope. So basically with the applied voltage, whatever is CD square from the formula you find out. And then you will be able to give that value. You understood? We have seen, I don't remember the formula, okay, so I'm not a devices person, so I don't remember those things by heart, but I think CD is equals to somewhat it was that under root Q W N something, the formula is there, right? So using that formula you try to solve that. So basically that V voltage is applied and then the reverse bias of 0.2. So V plus 0.2 will be there, and the CD value will be dependent as a square root of that voltage. So when you do CD square, it will become like have a proportional kind of thing with the V, and from there when you solve it you will get the a relation with CD square and V, and then from there the slope will come. Have you
Yes,
understood
ma'am.
the approach? Or if you do have doubt, then you can tell me.
Yes, yes,
Which
yes,
formula
yes.
I'm talking about you have understood, right? We have seen, I think, that formula. Okay. Okay. So I think there were a lot of questions from semiconductors in when the paper was from IIT Delhi, because I can see semiconductor questions. Yes. So one, two, three, four semiconductor questions, all of 2 marks, 8 marks here, and 9 marks, 1 mark question there, 9 marks. Then MOSFETs they have asked. Okay. Okay. So we shall start with small signal MOSFETs now. Okay. Today we will see the small signal analysis. Let me just share my screen first and then we'll start. Okay. So last class we had started the we had learned about the large signal model, right? So large signal model was done. Large signal model is nothing but the DC analysis, right? So in presence of DC, how your basically it is the DC analysis. So in presence of DC, how your MOSFET is behaving. Okay. So quickly let us revise that. So we saw the formula ID equals to half mu n COX W by L 2 times VGS minus VTH into VDS minus VDS square. Okay. This was one formula that we had seen. This was where in triode region. Okay. Next was ID is equals to half mu n COX W by L VGS minus VTH square 1 plus lambda VDS. This was in saturation. the channel length parameter will come into play after the device has reached saturation, right? So now in deep triode, what will happen? There was one more condition. So let me write the condition as well. So this is when the triode region is VGS will be greater than VTH, but VDS will be less than VGS minus VTH, right? Then the saturation is VGS will be greater than VTH, but VDS will be also greater than VGS minus VTH, right? VDS will be greater than VGS minus VTH. Okay. So now there was one more region which was deep triode region where VGS is greater than VTH, but VDS is very less than twice of VGS minus VTH. Okay, this was in deep triode. So in deep triode, what we say? That MOSFET behaves as a MOSFET follows Ohm's law or behaves as a resistor. And the resistance is given by R on equals to 1 upon mu n COX W by L VGS minus VTH. Okay. In all the cases, you will see that VGS is greater than VTH, because VGS, when it is greater than VTH, then only the MOSFET is on. And after the MOSFET is on, then only it can be in different regions, right? With MOSFET off, there cannot be any region. MOSFET is off, there is no story ahead. But if MOSFET is on, after that only there can be some region of operation. Okay. Now from here we will go to our next step. Okay, before that let us solve a simple problem. So I am giving you a circuit. Okay, so we have learned about biasing, right? Last class we saw biasing. We solved two problems also related to biasing, right? So all of you, I am assuming that you guys know KVL KCL. If you don't know KVL KCL, you can tell me, I will tell that also. Okay. So this is a MOSFET and you have to sketch you have to sketch the drain current versus V1. Okay. This is the drain current. So why I keep on doing this sketch and all, so that you know how the behavior of ID versus V1 is. We don't know what kind of questions will come on gate. So whatever comes, we need to be prepared. So I'm not saying that they will ask you to sketch something, but the question can be in any format and this can be helpful. Okay. So now you see here, first of all, which region MOSFET is in? Region of operation. How will you find out? You have to find out what? VDS, VGS and VTH, right? This we should know, then only we can tell which region of operation it is. Okay. Now what is VGS? This is gate, right? This is red I marked, this is plus, this is minus, this is VGS, right? Now this is VDS, plus minus, this is VDS. Okay. Now here what is happening, you see, I can put a KVL here. What is the KVL? I can go start from this point. I am marking green. Okay, I am starting from negative of VDS. Okay, and what I can do, I can simply come through this part back, right? So what I have done, minus VDS plus VGS equals to 0. So basically VDS equals to VGS. This you have seen in BJT also. This is called diode connected transistor, right? This is called diode connected transistor, where your gate and drain is connected to each other. Okay. In this case, VDS is VGS, and if VDS is VGS, that means obviously if I subtract VGS minus VTH, this will always be less than VDS, right? So this is always going to be satisfied. Always satisfies. So please keep on making notes as well. Diode connected transistor or MOSFET will always satisfy this condition, and therefore it is always in MOSFET. Whenever it is connected in diode connected format, it is always in saturation. Okay, it is always in saturation. That means which formula will I use? ID equals to half mu n COX W by L VGS minus VTH whole square. Okay, now I will write the value of VGS. What is VGS? Apply KVL from the known values. So whatever known is VDD and V1. Okay, so by known I don't mean numerical value. By known I mean what is the voltage that is applied. So I can put a KVL this way, right? The black path. That is the KVL. So what will VGS be? Minus VDD plus VGS plus V1 is 0. So VGS is VDD minus V1. This is my way of writing KVL equation. Yours can be different. As long as we are reaching to the same answer, there is no issue. Okay. So VGS is nothing but VDD minus V1. I hope you guys understood it. So let me just redraw it again so that here also you can see the MOSFET. Right. So I have applied one V1 at one terminal, I have applied VDD at other terminal, and I am asking what is the ID graph versus V1. V1 will vary from 0 to VDD. Okay. Now, what will happen? VGS we have found out. We know ID's equation. So ID is half mu n COX W by L VDD minus V1 minus VTH whole square. Right? That is what is going to happen. Okay. Now, here, when will ID be 0? ID will be 0 when this VDD minus V1 will be equal to what? VTH. That means V1 will be equal to what? VDD minus VTH. Is this clear? This is from the equation. This equation. So this will become 0 when VDD minus V1 minus VTH is 0. At that case, ID will be 0. So VDD minus V1 will be VTH. That means V1 will be VDD minus VTH. At this condition, ID becomes 0. MOSFET offs. Right? So, in my graph, the V1 will vary from 0 to VDD, as I have mentioned in the question that V1 varies from 0 to VDD. Now, ID follows a exponential path, square law, right? It is following square law. So ID is directly is proportional as what? V square, right? ID is proportional as V square, but we have to plot with V1. Now ID is proportional to VDD minus V1 square, right? So V1 is subtracted. That's why it is an inverse relationship. So what will happen? Like this. So this will be a maximum value, some value, okay, ID. And when it will be 0? It will be 0 when V1 has reached VDD minus VTH. So it will not go completely to VDD. Before only the MOSFET will get off and it will become, the current will become 0. Is this clear? Just look into the solution once from beginning to last. Look into it. Let me know if there are any doubts. Okay. So let me know once you are done and then I will proceed. Okay. So next is small signal model. Let's start with that. We'll draw the small signal model of the MOSFET. Okay. Okay. So now we had seen that ID varies with VDS, right? We saw it in last class. We saw this kind of a graph, right? And we said there is a slope here because of finite R naught and all those things we saw, right? So to show this variation, we can model a resistance R naught, which will be given by del ID by del VDS. Should not write it in small. It's, okay. First I write it like this. So del ID by del VDS inverse. Okay. To show the variation of ID versus VDS, we present a resistor, okay, which is given by this. Right. So there are two types of variations for ID. First is that ID varies with VGS, and we saw that graph also, which we say input characteristic, and there is a slope here. So this slope is what gives you the gain, the transconductance, GM. Okay, this is ID versus VGS. And then there is another ID which is not another ID, then there is another graph where ID versus VDS is there. So basically ID varies with VGS and VDS both, right? So we will represent both of these in a model so that we can model the MOSFET. So it's just like making a small model of that we used to do in schools. Okay. So we used to make a small model of something, right? Small model of a forest we are making, or small model of a house we are making. So basically what we try to do, we try to represent all the functions that the original thing can do. We try to replicate it, right? As better as we can replicate, the better performance it will be, because it will try to show us. So basically MOSFET is nothing but what? It's a basically device. So what physics people will do, they know the device physics. We have seen, right? First class when we saw the MOSFET structure, that is the original structure. But what will circuit people do? The people who are solving the circuits, they have to present a model which they can use for solving equations, basically for mathematically understanding the device. Okay. So what we do, we model the MOSFET. So this is the input terminal of the MOSFET, which is having VGS. Okay. So if this is the MOSFET, I'm doing it for NMOS. So this is the input, gate, source, drain. So this is VGS, this is VDS, right? So this is the gate, this is the source. Okay. And then what is happening? We are saying that the current ID, we are going to model the current ID which is flowing at the output, drain to source, right? So this is the drain terminal. Here we have the drain terminal, which is basically not connected to gate in any way. You can see in the symbol, right? But the source can be extended like this, because this is the entire thing is the source path. Okay. So now this is the drain to source voltage, VDS. Okay, so now what we are saying that the ID is varying with VGS as well as VDS. So that is why there is one current source which this direction, which is given by GM VGS. You can see it from the input characteristics which I have drawn here. Okay, the slope will be given by what? GM will be delta ID by delta VGS, right? So this is ID comes from GM VGS, and then there is a resistor R0 which models the variation of ID with respect to VDS, which is this one. Is this clear? Why the small signal is like this? So draw this small signal, write these equations. Okay, and after that I will proceed. Okay, so the gate is always reversed bias, right? I have just drawn the small signal for this symbol. There is nothing connected, right? So I think you mean something like this, that there is a DC voltage here, something like this you mean, right? So if you mean this, it is nothing but like this only, right? VGS doesn't matter. The gate is open circuited from here. There is no resistance. So in BJT there is a resistance here, but in MOSFET it is not there because it is we take the resistance to be infinite. It is a reverse bias junction, right? And that is why in a MOSFET it is all more reverse biased, and therefore the resistance is taken to be infinity. There is nothing in the gate to source. That is an open circuit. So basically when you put the DC voltages, I will put values there. I will put the source there and you can see the source. But right now I'm just writing that okay, this will be the gate to source voltage is the VDS. Okay. Did you get my point? I have not introduced any external voltage as of now. I'm just saying that it is biased. That's why I have not shown it. There will be some voltage applied to the input of the MOSFET. Okay. This will be the input side, this will be the output side. Some voltage will be applied, otherwise how will MOSFET work? Right now I have just shown you the model. Okay, is that out clear? Okay, so after this write a question. A MOSFET is biased at a drain current. A MOSFET is biased at a drain current of 0.5 milliampere. Mu and COX is given as 100. Oh, I'll write it in next line. Mu and COX is given as 100 microampere per volt square. W by L is 10. Lambda is given as 0.1 volt inverse. Mark all the value units. Okay, that is very important. W by L is aspect ratio. The units have cancelled out. All others are having units, right? So now what they have asked, calculate GM and R naught. Okay, so now we have seen that R naught is nothing but the variation of delta ID and delta VDS, and it is what gives this slope, right? You remember I had shown you that from channel length, if we vary, the slope varies, and at one point it is kind of near to the straight line. So R naught is actually very high there. In the last class we had seen that. So this is the slope which is basically telling you this R naught value, right? So we had seen in first class that not first class, last class I think. So GM, if considering the values given, this is the formula that you can use. We had seen three formulas of GM if you remember. Okay, and R naught is given by 1 by lambda ID, right? So now you can put it and get the values, solve it. So I hope you remember that. Please revise if you don't. GM, three formulas we had seen, and based on what you are given in the question, you can use any one of the formulas. and R naught is 1 by lambda ID. That also we had seen when we saw the channel length modulation. Okay, so now every value is there. Put it and let me know the answer. Has anybody solved? So this can be for 1 mark question, numerical answer type they can give. Okay. Anyone solving? Did anyone get the answer? So Chandrasekhar got 20 kilo ohm for R naught, I think, right? Okay. So anyone else got it? Jayesh, did you solve? GM value? So R naught is 20 kilo ohm, he is saying, okay. And GM, I think you will get 1 upon 1 kilo ohm or 1 milli Siemens or 1 milli ohm inverse. Okay. So the voltage gain, what is the voltage gain of the MOSFET? Let's see. We draw the small signal model like this, right? This is R naught, right? So now I am saying that the MOSFET is like this. Okay, I put some voltage here and I have put some voltage here. I have put a V in voltage here along with some biasing. Okay, and I'm taking the voltage V out from here. Okay, and I'm asking you what is AV? Voltage gain. Okay, so this will be V out. Here it is V in, right, in the small signal. Till here, any doubts? Please ask me. Even if it is a slightest doubt, you think that you are not able to understand, you tell me. Okay. So I have just put a V in, I have just put it across symbol. I have not put any bias resistors or anything as of now. I will do that later. Okay. And you can see the source is ground. Right. The source is grounded and there is a small signal model. So now what will happen? V in is equals to VGS. That you can see, right? V in is equals to VGS. Now let us apply KCL at this point. You can see the point. Okay, at V out. So what will be KCL value? It will be V out by R naught plus GM VGS equals to 0, right? Now you just put the value. V out by R naught is minus GM VGS. In place of VGS I am writing V in. Therefore AV is nothing but V out by V in minus GM R naught, right? This is the voltage gain of the MOSFET. Okay, so therefore in the earlier question GM is coming what? 1 upon 1 kilo ohm. R naught is coming what? 20 kilo ohm. So AV is what? 1 upon 1k into 20k giving you minus 20, right? So kilo ohm cancels out. That you have to be very careful about, right? So for this device dimensions that I had given you, for these conditions, see the green box, for these conditions you will get a value of 20 voltage gain. Understood? So now just write it down and let me know when I have to go. I will proceed after that. Okay, just write it down. I hope it is visible because Similar things will happen with PMOS as well. Okay, so I will quickly, I think I will show you one PMOS problem, and then you can just proceed with that. So PMOS is nothing but the voltage is basically change. The polarity of the voltage is basically change. So once you are done, let me know. I will quickly show the PMOS as well, and then we will move forward. So I'm moving forward then after this. Okay. So PMOS, let me draw. So this was the NMOS, right? This is how NMOS will be biased. So this will be VDD. Here there will be some VIN, and this will be grounded. Okay. This is how NMOS is done. Now for PMOS, the source will be at higher potential, right? So source is at higher potential. There is a VIN here, and the drain will be grounded. Okay, so remember we had said that the source and drain of the MOSFET is decided by the potential, and in NMOS the higher potential is that drain, and in PMOS the higher potential it is source, right? So now what will happen to the small signal? It is simple. It will be like the way it was. So let us just first draw the small signal. Okay, the current direction is now from source to drain, right? This is the source terminal here. This is the source terminal here, right? VSG will be positive, so plus minus VSG I am writing here. Okay, and then what I am doing is I will short the drain to ground. Okay, yeah, and I am taking the output from here. So sorry, is there a mistake? No, that is fine. Okay, so the output will be from source itself. Okay, so for PMOS it is like this. Okay, so now I will show you one more model which is like this. Sorry. So the MOSFETs model, okay, and we'll see the diode connected model like this. Okay, and now we will be drawing the small signal of this model. So what will be the small signal? Everything will be same except that there will be one short connection from here to here, right? So let me draw. And here I am saying that there is some input as well, right? So now the gate and drain is going to be short. Okay, the gate and drain is short, you can see it. Now in this, if I ask you what is the value of R out, so R out we find with Thevenin concept, right? So what is Thevenin's concept? That you apply a voltage source VDC at the output, from where there is a current IDC going in, and at that case V in should be 0. Okay, so now let's solve this. Okay, so let's solve this. So what will happen, if I put a KVL here in this node, if I put a KVL, VDC by R0 plus GMVGS, okay, plus GMVGS equals to IDC, right? Now the question is, what is VGS? So what is VGS? What do you guys think? What is VGS? So you can now put a KVL in this, right? Because it is now shorted, a KVL here is possible, the green line. Right? So there, that means VDC equals to VGS, right? So VDC, if I take common from here, I get 1 by R0 plus GM equals to IDC, and I get R out as VDC by IDC equals to 1 by R out plus GM. So this was a similar question which was, again I am saying that this was a question which was again asked. This I have written wrong. Okay, this is inverse, right? So this inverse. So R out is 1 upon 1 by R0 plus GM. And a similar kind of question was asked by I think in GATE. So we will do that question later. But here you see R out is coming as 1 by R0 plus GM. What does it mean? GM is transconductance, right? And 1 by R0 is also a transconductance parameter. Both of them, these are what? Transconductance parameter. This is the transconductance of MOSFET. And this is also a transconductance parameter, right? Inverse of resistance. So inverse of resistance, right? So that means I am doing R out equals to 1 upon, let's say, capital GM. That means capital GM is nothing but 1 by R0 plus GM. Now you will remember that whenever the resistances are in parallel like this, so if there are two resistances in parallel, R1, R2, what is the total resistance? R1 parallel R2, right? So R1, R2 by R1 plus R2. Okay. But if I say what is the G, what is G? That is the transconductance. Then you can write 1 by R1 plus 1 by R2. Transconductance of R1 and transconductance of R2 will get added, and that will be the total transconductance. So resistance in parallel will get this parallel combination, and transconductance in parallel adds up. This is from network theory, right? This is basically nothing but the inverse of what you have just written as R, right? So it makes sense. G is equals to R inverse. This is clear or not? Please let me know. Is this clear? I'm taking it that you guys have this concept. Okay. So now, what is happening here in the MOSFET? In the MOSFET also, GM is 1 by R0 plus GM, right? That means R out is therefore 1 upon 1 by R0 plus GM. So, which makes sense because this is nothing but a parallel combination only now, right? Direct parallel combination. since we have shorted that, and therefore this is coming as a direct parallel combination. And therefore you must remember this result. It is an important result that in a diode connected load, whether it is a PMOS or an NMOS, doesn't matter, the R out is always 1 by R naught plus GM. Okay, 1 by R naught, sorry, again I messed up, 1 by R naught parallel to GM. Okay, and since 1 by R naught is a higher value than GM, normally 1 by R naught will be greater than GM, usually. Therefore R out turns out to be approximately equal to GM. This you should remember. Okay, is this fine? R out is always, R naught is always in the order of some kilo ohms. Okay, so that's how it turns out to be. So normally this is what you should consider, the first one. Okay, after approximation the last one comes. R out is 1 by GM, not GM, 1 by GM. Please rewrite this. I have written it the opposite way. Okay, so R out is R naught parallel with 1 by GM. So R out is very greater than 1 by GM, and that's why R out is approximately equal to 1 by GM. Okay. After your guys are done with this, please let me know. We will do some questions. So if lambda tends to 0, that means R naught will tend to infinity, and in that case we take 1 by GM to be this thing. Okay, so in that case R naught will be very greater than 1 by GM, and then you can take this approximation. So please let me know once you are done with this. We will quickly do one small signal model of a bit complicated circuit, and then we will just finish the class. Okay. Chandrasekhar, can you unmute and tell me which part you want to get explained?
The last part, R out.
So we saw this thing, right? This you understood, right? Why I have written it
Yes.
like this? This one is fine? Okay. So that means I can write R out as, so if GM is the addition of the transconductance, that means R out will be parallel combination of this, right? Which is what I showed in the with the resistors.
Yes, ma'am. Yes, ma'am.
Is this fine? With R1, R2 I showed now. This is fine. So this is just the R out. So if now if lambda tends to 0, that means channel length modulation is not present. It's an ideal circuit. Therefore R naught tends to infinity. Therefore R out is approximately equal
Yes,
to 1 by G.
ma'am,
Now is
can
it
you
fine?
zoom in?
Okay. Please let me know after you guys have written. I will go into the small signal of other. And after doing this one small signal, next class we will do another small signal, and then we will proceed to the MOSFET questions that were asked. Okay. And after that we will do amplifiers. So please let me know once you guys are done. We have only, I think, 5-10 minutes we are left. I wanted to do one small signal analysis. So I hope others are also participating. Okay. So if you guys have any issues, you let me know, because very few of you have joined today. So I think only 4 of you have joined today. Should I move forward? Is it done? Okay then. So let us draw the small signal of this circuit. So let us draw this circuit first. Okay, this is the simplest circuit. CMOS amplifier. Sorry, not CMOS amplifier. This is your common source amplifier. So CS amplifier with resistive load. Okay, and in the small signal is just like what we had seen, plus minus VGS, GM VGS, R naught, and now since you see this point is drain, right? The V out point is drain, and VDD is grounded because we are doing the small signal analysis. So all the large signal will be 0. Okay, all the DC will be 0. So that I forgot to mention, that is why that terminal goes to ground. Okay, so now this will be ground and the RD is between the drain and ground. Okay, so this does not mean that the RD is between drain and source. This means the RD is actually between, so let me draw it like this, otherwise you guys will get confused. So RD is like this. Okay, from drain to ground. So VDD becomes 0 volts. Okay, and here there is some signal V in being applied, which is a small signal, and V out, which is again a small signal, and whatever the DC bias will be, that has become 0. Okay, so this is the simplest one. Please quickly take a screenshot or something so that I can show you the next one as well. So take a screenshot of this. Okay, take a snap, and next let me just go to the next question. So these circuits I have taken from Razavi's microelectronics book, which is the basics of analogs book. Okay, not the design one. The microelectronics book I have taken this from the back exercises. Now you see there are two MOSFETs, right? There are two MOSFETs. Now you have to do the small signal. So what will you do? So the way I do is that I separately make the small signals first. Okay. So let me just make small signal first of M1, GM1, VGS1, RO1. Then there is RD. Here there is a V out. Here it is plus minus VGS1. Now I will again do a VGS2. Plus minus VGS2. GM2, VGS2, R out 2. Right? Now you see this node M of M2 source is grounded. So I will ground it, right? I have grounded it. This I have joined. This is ground. Now this voltage is plus minus VGS2, which is equal to V in, right? This is equal to V in. And for M1, what is this voltage of source? This is nothing but V in minus VGS1, right? So the gate of M1 is also receiving V in, but not with respect to source, with respect to ground. The gate of M1 is receiving V in with respect to ground. So V in is here. This is the gate. So V in is here, right? And V in is also here. And this is with respect to what? Ground. Is this clear? So now you see, in the small signal, V in is equals to what? V in is equals to VGS2, right? And then what I will do again, this here you see in the small signal I am making a line, a thick line I have made, right? This one. So this node is nothing but what? The source of the M1. Here in the circuit also, this is the source of the M1, which is connected to the drain of the M2. This is the drain of the M2. So source is connected to the drain. So we just have a line here. There is a connection here. Done. This is again connected here. So let me properly do it. Okay. So just make this. Okay. So this is the small signal. So I deliberately did it so that you guys can now analyze it. So I did it very quickly. So analyze it, and then wanted to do the R out analysis, but let me just stop here. You just analyze how I have drawn the small signal model. Okay. And after that, you guys try to draw another small signal model of, I'll give you time to note it down, don't worry. So I'll give you one more circuit. Try to draw the small signal of this circuit, okay? So after we do this kind of practices for small signal, we won't need to draw the small signal in the exam. We can just look into the circuit and tell what will be the GM, what will be the R0, what will be the voltage gain. That is possible. But first we have to learn the small signal. So this is your homework, I would say. Try to analyze, and this is also the small signal that I have drawn, that also you analyze. Okay, so I think it's better, this resolution is better. So quickly try to copy it down. So in next class we will see the R out value, how to find here, GM value, how to find, and we will find the voltage gain like that. And after that we will solve the questions that have come in the gate. Okay, gate previous year. So please do this and let me know if when you guys are done. Okay. Okay, Chandrasekhar, I will try to solve that. Okay. Recorded videos are available in YouTube. I put them in the links. Okay. And they will be available in NPTEL website as well. But I always recommend you to join the live class so that it is an interactive session, because recordings and YouTube videos, you can always Google search and see YouTube videos on every subject, but the interaction is absent there. They don't interact with you. So since in the live classes interaction is happening, you guys should take advantage of it, not only in my class but in all the classes that are happening for GATE subjects. You should try to take advantage of it. and join the class. Okay. So is this done? Okay, then in next class, then I will. So what Chandrasekhar had asked was, I'll tell you. Uh, you guys can also see GATE 2020 in the technical questions. Question number 7, and I think it was question number 30. Is it? Uh, it was question number 31. Okay. So you guys can also see this two questions. Okay. So next class I will try to solve these two, and then we will move forward with MOSFETs. Okay. Okay, then if there is no further doubts or question, then I'll end the session now.